Alright, I bungled up the last test, so we're going to have to run through them again, just for a couple of guys on the forums, in regards to our U-Butte transformer here. Okay, so a little rundown first. I've changed the gate resistance and dropped it down to 100 ohms on each FET, as you can see there. I have a 1 ohm 20 watt resistor in series with our primary coil and drive unit, just for some measurements later on. And I have a 2.2 ohm resistor here. It measures 2.2 ohms, and it is off our secondary coil going to our light bulb. You will also see a couple of resistors there. One is in one direction and one is in the other, and that is for a test a little later on in this video as well. So now we can measure the current, or we can see the current flowing through our primary coil, and also the current flowing through or out from our secondary coil to our load, which is our bulb. Our signal generator is set to 7 kHz, 10% duty cycle on the square wave, 12 volts peak to peak, but on request I've offset it by 4 volts. So we get roughly 8 to 9 volts at the gates. So, my impedance is set to 0. I can set it to 50 ohms, but I'll leave it at 0. So that's pretty much well it for our signal generator. Our scope, okay, for test A, for TK, I have channel A, or the yellow trace. Ground is on the negative of our input, and the probe is on the positive input from the signal generator. And trace channel B, or our blue trace, is once again with the ground reference on negative, and the probe is on the positive side. I have it after the diode, so there'll be a slight voltage drop. So as we can see here, nothing on a yellow trace because the signal generator is not turned on, but we have 12.8 volts on our blue trace, which is our battery voltage minus the voltage drop on our input diode. So that is going to be called test A. So as you get the right scope shot for the right test. Okay, so channel A, yellow trace, 5 volts per division, and channel B, our blue trace, is at 10 volts per division, 7 kHz. So you can see now I have roughly 2.5 volts below, or 2 volts below, and we have 10 volts on the forward side going to our gates from our signal generator. And of course that is the signal from the input, with our little ring ding dinging going on in there. So that is test A, and I will print that for you. Now for test B, we simply have to move this probe here over to the other side of our coil, from what I understood, like so. Now I have this clip lead going from our primary coil to one leg of our secondary coil in there, also as requested. So that is what we now have across the scope. That is going to be test B, and I will print that off as test B. Okay, so and not forgetting we have our 1 ohm resistor in line there. Alright, so that's those two tests out of the way. Next we're going to have a look at the voltage across and the current flowing through our load, and see what is happening there. And then after that we're going to have a look at the current flowing through our primary when it's switched on and then switches off, compared to the current flowing through our secondary when the primary is switched on and switched off while driving the load. So I'll go ahead, shift everything around, and we'll be back shortly. Alright, so everything's the same. I'm leaving this link between the primary coil and the secondary coil in place throughout the test. So this is our CSR for our output from our secondary going to the globe, and at the moment you'll see I've bypassed both these diodes. So when the diodes come into play, we're going to have to take into account, there's only about a 0.4 volt drop across those diodes, but something to take into account. The only thing I have changed is I'm now triggering off the secondary coil around the outside of our toroid, so as we don't lose our trigger source when I go and change things around here, and it keeps our scope shot very stable. Alright, so our blue channel here on the scope is across our 2.2 ohm resistor, and our yellow channel is basically across the coil and the resistor, or across the globe, whichever you like. So here's the scope shot at the moment. Now I've dropped the voltage down on channel 2 to 2 volts and channel 1 to 2 volts per division, and channel 2 is at 200 millivolts per division. And as you can see in the scope shot, obviously this is our on time for our primary, and this section here, being the other 90%, is the off time, and you will see a slight ringing there. If I open up the trace a bit, it is got a lot of ringing there, for about 3/4 of a division. But this is the part I've always been interested in. You can see during the off time there is indeed current flowing through that bulb, and of course that is the voltage across the bulb during the off time. So when the primary coil switches off, both the current and the voltage change in direction or polarity. The current's changing in direction, the voltage has changed in polarity. So that's what we have there. So what we're going to do now is drive the globe off the top side. So the globe is going to be driven off of the current from our secondary when the primary is switched on, and we do that simply by putting our output from our secondary on the front side of the diode, so it can only receive the current flow in one direction. So you can still see the voltage across our coil resistor combo, and not the light bulb, because at this point in time down the bottom here, as you can see, there is no current flowing through the bulb because of the diode, but we can still see the voltage across the coil and resistor combo, of course. So our globe is now being driven from this current source here, the high side or the forward side, and as you can see, no current flowing through the globe when our primary coil is switched off. So what we're going to do now is we're going to run this globe, so we swap this clip lead over to the diode that's facing the other direction, so our globe will only be receiving the current that is produced by the secondary when the primary is switched off. So we'll go ahead and do that, and of course the voltage isn't as high, and we have our small voltage drop across our diode, but as you can see, the light is still going. So as you can see, other than the ringing when the transformer switches off, the current when the transformer is on is 0. We get a little spike of current when the primary first switches on, and then because it's not driving the globe, we get in between the 10% duty cycle that it's on, we get no current flowing. But as you can see, once our primary has switched off here, getting a little ring in the secondary, and then a nice steady current flow right through until the primary switches back on again, and of course a voltage across our globe now, because we have current flowing through it. And this is during the off state of our primary, and as you can clearly see, the current and the power is flowing through that globe the whole time the primary is off, which is an indication that the magnetic field in the center of our toroid is just not totally collapsing before the next cycle. In fact, that is very, very slow. So that globe's now being driven from the well, what you would call normally the inductive kickback. However, our inductive kickback is normally very, very short, but in this case, in the center of this core, the magnetic field is soldering on. It's simply not collapsing completely before the next on state of the primary. And we can drop this down to 5%. Not quite as bright, of course, but you can still see that for 95% of the off time on the primary, current is still flowing through that globe. So I'm afraid the magnetic field isn't at strongest around the outside of a toroid core, or in the centre near the hole or the inner diameter. There's a extremely powerful magnetic field in the centre of that core, and it just doesn't want to die. I'm just lifting that back up to the 10% duty cycle. So what we're going to do next is have a look at what's happening in our primary as far as current flow goes, and the current that's coming out of our secondary. We'll see if there's still current flowing through the primary, because it is actually a current loop with that diode that's in the system, and that's going to give you a good idea of how the magnetic field is collapsing down through the core, and it seems to get towards the middle and just slow right down. Alright, so I'll go ahead and swap all this around, and we'll come back and have a look at the current flow in the primary and the secondary during the on and off states. Okay, so we have our blue channel across our 1 ohm 20 watt resistor. I still have the link between the primary and the secondary hooked up, and both scopes, both the grounds on the scope are also hooked to that link. And our yellow channel, channel A, is across our 2.2 ohm resistor, which is showing us the current into our load from our secondary, and of course this resistor is showing us the current flowing through the primary. So at the moment we've bypassed the diodes once again, and we're simply driving the globe, and the globe doesn't look as bright because I've dropped the duty cycle down to 5%, so I can stretch this right out and show the effect a little more clearly, so a little less power getting to the system. Okay, so I have my U-boot little pen here. The blue trace is our primary current, and as you can see, when it switches on we get a spike in current, then it switches off and we get this ringing for a very brief period of time. Try and keep the camera straight. Okay. Then you'll see during the off time there is no current at all across the primary coil. However, there is still current flowing across the secondary coil. So what we're going to do now is we'll hook the diode up to allow the current in the forward direction, or the positive direction, whatever you want to call it. That's what's running the globe now. And as you can see, both the primary and secondary current are pretty much in phase. And then during the off time, of course, they both have nothing now because we have put the diode in place, so current simply cannot flow in the other direction. So we're now going to change it over, so now that globe there is only receiving the what we would normally call the inductive kickback spike that seems to last 95% of the cycle, or the 95% off time, and now we will not have any current in the forward direction. So as you can see here, once again, the current surge when the primary switches on. When it switches off we get this little ring, and then the current in the primary flatlines. There's absolutely nothing there, but the current in the secondary continues to flow all the way up until the primary switches on again. So the off time, our inductive kickback, is what is driving that globe, but normally you would have, with a load like that, the inductive kickback would be a very sharp spike, and then it would also flatline. But as we can clearly see here, the current continues flowing right on until the next switch on time. So I really have no idea how those magnetic fields in the centre of the toroid can continue on for so long and continue to produce current. And like I said, we are very low in power here. 47 milliamps at the moment is all we're using to fire up our primary coil. So yeah, I don't know what's going on in the middle of those toroid cores, but that magnetic field that's in the centre somehow just keeps going and going and going. So what we're going to do now is I'll swap all this from the internal coil to the external coil, and we'll come back and have a look at that. Alright, so now we are running our globe from our secondary that's wound around the outside next to the primary. The blue channel is in the same position. I have removed the resistor from our internal secondary and put it on the external secondary just to make sure we're using the right resistor of the exact same value, blah blah blah. And basically the rest is the same setup. So our yellow trace is showing us the current from the secondary coil on the outside, and I'm seeing much more what I would have expected. Is when our coil switches off, we get our little inductive kickback current going to the globe. It seems to be a little late for some reason, I don't know why, but we are at 25 microseconds per division, so there's about a 12 microsecond delay there. I'm triggering from one of my internal coils, so as once again we can keep everything stable. But if we switch to the diode, so we're driving our light from the inductive kickback as per normal, and we'll get rid of channel 2 so we can see a little more clearly, and we'll lift that up. We can indeed see our little inductive kickback current flowing through there, but it is very poor, because as you would have seen in other videos, coupling between the primary and secondary around the outside is not so good for some reason, and one would have thought it would be the best. But that there, the big spike, that is from our primary coil switching on and off, and then we get our current flowing from our inductive kickback spike. I'll turn the channel A off so you can see. So as you can see from that, and that, when the coil switches off, we get our little bit of ring is when we're getting the current flowing through. But after that, as per normal situation, it is very flat. So that's what we would expect normally in a normal situation. However, that's not the situation with the internal coils for some reason. I still have this on 5% duty cycle as we did in the last test. Let's crank it up to 10. And you can see once again so that little spike there is the coil switching on, and our big one is when the coil switches off, we get our inductive kickback current flow, and then we have nothing until the next pulse. So that is normal. But for some reason the internal coils do not want to play normal. So coil on, primary coil on, current going through the secondary, primary coil off, and that is our inductive kickback current just after that, and then it flatlines until the next pulse. Whereas our internal coil, the current keeps on continuing right through until the next pulse for some reason. I do not know why. So there you go. That's about as clear as we can make it. So I'll go ahead and get this all joined and spliced and uploaded so you can have a look. Thanks guys. Okay, so I'm just going to tack this on the end of the video. What I want to do is look at the current flowing through both the outer and inner secondaries at the same time. So we've simply grabbed another resistor of the same value as the one we had there. This globe, as it was before, is running on the outer secondary. This one is running on the inner secondary. You can see the difference quite clearly. And that's pretty much well it. So the yellow trace is the current flow through the outer secondary, and the blue trace is the current flowing through the inner secondary. So if we open that up a bit and decrease our voltage divisions so we can get a clear look at what's going on. Actually, I'll increase those divisions again so we can get it in the screen. Right, so as we've seen before, the current through the outer secondary is pretty much well matched excuse me, to the current flowing through the primary, because it is wound right next to it. So we can say that that's our primary switching on, that is our on time. The primary switch is off, gets our ring, and that is the current being collected from the secondary from that ring. That would be our inductive kickback current, and that would be a normal situation, the yellow trace. However, the internal coil, as you can see, the current builds on a curve, so a little more slowly, peaks higher, and you can see the little jitters there from the ringing of the primary, but then as we've seen in all other tests, that current continues to flow at nearly a very even rate until the next cycle starts, or the primary coil switches on again. So how is this doing this? How do we get that? Is almost a very steady DC current until next switch on, which then of course when it switches on the current changes direction. So this is very interesting. It doesn't happen around the outside, only in the centre of the toroid core for some reason, and I think it's well worth investigating a little more. Alright, that's it. Let me go and get this all joined together so you guys can have a look-see. Thanks mate.